All right, in this video, we're going to look at some pictures to get a conceptual idea for when a function fails to be differentiable just from thinking about the graph of the function. So either a graph is provided or you just visualize what the graph looks like. So the first thing that we want to think about is that when we think about the derivative of a function at a point, I'm going to use the point x equals c here. I'm just going to write down that definition, which you should have memorized. So it is defined to be limit as h approaches 0, f of, here I'm using x equals c, so c plus h minus f of c all over h. And so we're going to focus on graphs, but the reason a function might fail to be differentiable based on its graph is always going to come back to some part of this definition that is breaking down. So we're going to look at a couple of different ways that might happen. All right, so I want to focus just for a second on this definition and kind of think about the pieces of it. So there's a limit to evaluate, but before you evaluate a limit, you've got to set up this quotient. So we did a lot of problems with equations where we set up this difference quotient and did a bunch of algebra and then evaluated the limit. But let's think about when might you not even be able to set up this quotient. That would be one reason that this derivative might fail to exist, let alone what's happening with the limit if you can't even set this up. So at one sort of level might be that you can't do this part. So that says f of c. So what that is a point at x equals c. So that's one reason that you might have a function that fails to be differentiable at a point. Right? So there's a lot of different graphs where you might have a function where there's no point at some value, x equals c. It could be, I'm just going to label a place here, c, that the function just has like a hole in the graph at x equals c. So the function exists on both sides of x equals c, but there's no actual point at x equals c. It could be that you have perhaps a vertical asymptote on the graph at x equals c, and whatever the function might do on either side, maybe both sides go up to positive infinity, or maybe they do different things on each side. But these are just some examples of graphs where you have no point at x equals c. So another way to say that might be to say that x equals c is not in the domain of the function. All right, so that's certainly one way that we might have this limit fail to exist. But there's a lot of other ways. And so you want to be able to look at graphs and say, oh, there's no derivative at that place because I see these sort of red flags right away. So that's a handy skill to have. OK, so besides no point at x equals c, there might be reasons that this limit might fail to exist. Does not exist for other reasons besides f of c not existing. All right, so what are some of those other reasons that this limit might fail to exist? And there's a lot of different ones here, so I'm just going to draw some, not necessarily in any particular order, but just kind of connecting to this idea that we have over here. It could be that we have maybe a graph of a function, and we have a point at x equals c, but a function that's doing different things on either side of x equals c. So there's a lot of ways that might happen. I could have a function, maybe a piecewise function, where the pieces don't connect. Right? So why would that limit fail to exist at x equals c if I have this piecewise function where the pieces don't connect at x equals c? Well, if you think about the visualizations that we looked at in a previous video where we looked at, on Desmos, some slopes of some tangent lines, and we drug that second point closer to our first point, and just kind of visualize what that would look like if I look at a graph like this. Let me get a brighter color so we can see here. So at x equals c, we have a point here. And then if I take that second point to be, say, on one side of x equals c, and think about that secant line and then let that second point slide, you can see that you're going to be able to get a slope on that side. And so whatever the slope of that tangent line is at that point on that one side. So on this one, this picture, the limit as h approaches 0 from the right of this quotient is okay. But if you think about the other side, so I've got my point at x equals c, and then I take my second point on the other side, so on this other piece, and I think about the slope of that secant line, and then I let that second point slide in closer and closer. Remember, it's not actually going to touch my x equals c, but it's going to get closer and closer. And so you can visualize what you're going to get here is steeper and steeper and steeper lines. And so for this picture that I have, the limit as h approaches 0 from the left, so remember h is the distance between those 2 points, as that's approaching 0 from the left, I'm getting these steeper and steeper and steeper tangent lines, and so those slopes are approaching positive infinity on this side. So I've got different slopes on different sides. There's several ways that that might look. This is a picture of a discontinuity that causes different slopes on different sides. We've talked about a theorem about continuity and differentiability, that differentiability implies continuity, so discontinuity implies not differentiable. These, by the way, are also some other pictures of ways that a function might be discontinuous at x equals c. But there are some other ways too, and where I said the function's doing different things on either side of x equals c, and remembering that this difference quotient really represents a slope. So I'm going to draw just some other pictures of ways that we might have different slopes on either side of x equals c. So sort of the quintessential picture of that, this is kind of a classic picture where a lot of places you might look give this picture of this function, y equals absolute value of x function. And here we're focusing on the point at 0. So in this case, our c would be 0. And then if I think about slopes of secant lines and let that second point slide in, so you can see that on one side, if I take my initial point at 0 and then my second point on the right, and I look at the slope of that line, and then as I let that second point slide in toward the first one, those slopes on that side are always going to be positive 1 on the right side of x equals 1 for this specific function, y equals absolute value of x. And then if I think about the other side of that point, though, so when h is approaching 0 from the left, that distance on the other side, so that second point is on the other side here, and I think about that slope, and I let that second point slide toward my x equals c. On this side, we're going to get slopes of negative 1. And since these slopes don't agree as h approaches 0 from the right and h approaches 0 from the left, those slopes don't agree. So this overall limit does not agree. So kind of the idea here is that I have different slopes on each side of x equals c. And on this graph, it's easy to see that you have different slopes. One is a positive slope and one is a negative slope, and it's very easy to see that they're different slopes. It can be more subtle than that. So if you think about perhaps a piecewise function where you've got maybe straight lines, so it's easy to think about slope, but I've got, say, one with a slope of, say, positive 1 on one side, and then on the other side, maybe I have a slope that's very, very close to 1, and so also positive, but just a little bit less, so say 0.9, right? And it can be very hard to see that from a graph. But if I do have different slopes on each side, so I would need an equation or some other information to be sure I know that I have different slopes on each side. So this can be hard to see, that you have different slopes on each side. But sometimes it's very obvious because you have something like this, a sharp corner, sometimes people say, or just a corner, where I have a corner at that point. So when I see those corners on that graph, I would say, oh, I know that I have different slopes on each side, so that function's not differentiable at that point. It can be differentiable at lots of other points, but at that point where you have that sharp corner. All right, so we've really talked about a couple different ways here, although I have several different pictures. Discontinuity right? So that can happen for a couple different reasons. More pictures even than I drew here, but discontinuity kind of encompasses all of this, or corner, where I have different slopes on each side. There's one more way that I want to talk about, so I'll draw a picture for that over here. And again, there are several pictures that I could draw for this. But the other thing is that I could get that this limit, instead of approaching a number, that this limit perhaps approaches infinity or maybe negative infinity. And so if I think about that slope approaching infinity, one picture that we might think about like that is where I have a graph of a function where if you think about the slope as you come along this curve and you get close to that point and then move back along there, or like we did with these others, you can think about picking a point there and then another point on one side or the other and letting that second point slide in, and think about those slopes of those lines getting steeper and steeper and steeper. So the slope here is approaching positive infinity in this graph. Another way to talk about that is that we could say what we actually have here is a vertical tangent line. All right, and then there of course can be combinations of these. So I mentioned corner, where I have different slopes on each side. I could have something where I have different slopes on each side, but the slopes on each side are approaching infinity or negative infinity. Our textbook shows a picture of that and labels that as a cusp. So where you might have a slope approaching positive infinity on one side and negative infinity on the other. It looks like a corner. It's just that the slopes are getting infinitely large as you approach that point. Again, these are difficult. This sharp corner is not difficult to see, but the vertical tangent can be difficult to see on a graph, whether that slope just gets really steep but stays finite, or whether that slope approaches positive infinity. So these two that I put over here are ones that can really be kind of hard to see on a graph unless you have a function equation or some more information where you can calculate something about slopes, whether the slope is just really large or really is approaching infinity, or whether these slopes are the same or just look very close to being the same. Those can be kind of hard to see. All right, but you do want some visual kind of ideas about looking at graphs and being able to see where the derivative might not exist at a point. So discontinuity, different slopes on each side, several different ways that that might happen. And then the other big deal one is vertical tangent. Again, that can be hard to see unless you have been told that there's a vertical tangent there at that point. Or maybe if you have a function equation, you can look a little bit about the derivative at a specific point. All right, there are some more pictures in your textbook of all kinds of different things. And of course, I could draw lots more pictures here, but I'm kind of out of space. So think about these pictures. Make sure you have good mental concept of that. Maybe also look at the ones in your textbook and then try some homework.